Great. Okay. So last class, um, I tried to quickly do particle filters, but I think I didn't do a good job. So I thought that I'll redo quickly again. I floated the core idea to you, but I thought I'll just redo it quickly. But this time you have the pre-notes on the web page. So I hope you've downloaded the pre-notes. Guys, give me a sense. How are you using the pre-notes? Are you printing it? Are you downloading it into your iPad, or are you not really using it too much? Can you give me a sense?
I usually download it at the beginning, kind of like or before class, and fill it in as we go.
So you have an iPad or a tablet?
Yeah.
Okay.
Yeah.
Okay. I just use it. Derek says I just use it as a preview to what's going to be covered. Okay, I see. Jian Hao says I'm not using it. Okay. Um, okay, I see. But I'm hoping it's still useful for those who are using iPads or printing it out. I'm sure it's useful. Okay, so I'll continue to do pre-notes. With that, let's get started. Today's plan is spend the first 15-20 minutes on particle filters, maybe particle filters, and quickly give you an idea of SLAM. We are not going to do this mathematically, but let me tell you, if you understand hidden Markov models very well, it should be possible. Shouldn't be difficult to build up on top of that if you want to read particle filters, if you want to understand the math for particle filters. SLAM gets harder, but particle filters you should be able to understand, and SLAM builds on top of that. But I just want to give you the intuitions today, and along with the HMM math and these intuitions, I think you're in a good position to do particle filters and SLAM if you ever have to do maybe in your grad school, or if you join some industry where they're doing motion tracking, self-driving cars, etc. Okay. And then in the second half, or the second 2/3 of the class today, we are going to get started with the basics of optimization. And that would lead us to something. We are going to look into acoustics, where we're going to do adaptive filtering, noise cancellation, and various other topics downstream. Okay. So now in this mobile computing course, we started with GPS, then we did Wi-Fi, wireless, localization, then we moved to IMU, then we did motion tracking, gesture recognition, applications of HMM, and now we are going to move on to the other important sensor, which is the microphone, and talk about various applications around acoustics. And finally, we're going to look at a quick one around cameras, and then we're going to end the course. So essentially, we're looking at all the important sensors in IoT and mobile computing platforms, and basically applications and algorithms around these sensors. That's the structure of the course. Okay, good. Any questions thus far? Good. Okay, so let's get started. We talked about this last time, particle filter. The motivation comes from the following. HMM is in discrete space, but most real life applications are in continuous space, right? A self-driving car, when it's moving, moving, you want to track the self-driving car. The road, the highway is not discretized into tiles. You need to have algorithms for continuous space. Second, HMM needs transition probability matrix. That's the motion model that we used. But can we generalize this more? Can we say, as long as we have some function where the state sk is some function of state k minus 1, sk minus 1, can we develop a model for any function g, right? That's something that HMMs don't do. HMMs have this matrix that you need to always give. So the question is, what can we do if we want any function g? Third, HMMs thus far have not modeled noise, but the most general version for HMMs would be where the measurement is a function of the state plus some noise. And also the state transition, the current state is a function of the previous state plus some noise. So can we model all kinds of noise? That is something that we also want to generalize to. And finally, an important one is computation cost of HMM is very high. And someone tell me why the computation cost is so high. Even though it's a dynamic program, even then the computation cost is pretty high. And tell me why. Someone?
You're sort of tracking like every I think it grows exponentially when you the number of positions when you track every trajectory.
You're tracking every trajectory regardless of how probable this trajectory is. Okay, great. So this is where particle filters come in, and particles filter want to generalize HMMs. They want to make it continuous space. Any function f and g, where f and g are the measurement and the state transition functions, and any noise. This noise can be Gaussian, this noise can be some other distribution, any distribution. And you want to reduce computation as necessary. Okay. If you say that I want to run this HMM, I want to run a particle filter on a mobile phone, sure, you can do that. You're of course going to lose accuracy of tracking, but you can do that. Okay. HMMs you cannot, right? The HMM basic model is you have to track all the trajectories. That's going to take a fixed amount of computation. But particle filter gives you this knob. If you want to run this on a smartwatch, sure, you can even cut it down, right? Of course, you're going to lose accuracy, but you have the ability to bring down the computation as necessary. Okay. So with that, let's get started with particle filter. This is our pre-notes for today's lecture. So basic idea is the following. Model the location of the object with a particle at that location. And again, it'll become clear. But essentially we are saying is, if we think that we know that this person is at this location, then we'll put a bunch of particles at that location. Okay. So since we know the object's location probabilistically, since we do not know exactly where the object is or exactly where the robot is, we only know it probabilistically, because remember, P of Sk is basically P of Sk equals L1, L2, so on, LR. This is what we did for hidden Markov models, right? So the Sk, which is the state of the particle at time k, could take all values L1 to LR, which means we know the particle's state or the location probabilistically, right? So in particle filter, what we are going to do is we are going to put a particle at possible locations of where the object can be. Okay. So I'm going to since we know the object's location probabilistically, let's scatter n particles at most likely initial locations. Most likely initial locations. Oops. Locations. And then compute a weight for each particle based on its agreement with motion models and measurement. Okay. We are going to put we're going to scatter particles in the initial location, and then we are going to update the weights of the particles. Okay, if it doesn't make sense, don't worry, because we are going to go step by step and look at the particle filter. Okay. But the only thing to remember is at any point in time, the particles, the scattering of the particles capture how my belief, but basically captures my belief about the object location in space. Okay, this is the particles capture my belief about the object about how the object locations are distributed over space. Okay, if that didn't make sense, no problem. Let's look at the example. Let's look at it step by step, and I think it'll all come together. Okay. Let's say you know that the robot is over here initially. X-axis is space, and it's continuous. It's no longer L1, L2, L3, L4. Okay. And we know, for example, let's assume that we know the robot's location initially. And let's say your computation, the CPU that you have, is that determines how many particles you can support. Let's say you can support n particles. Okay. So you take n particles and you put all of them in this initial location. Okay. And this essentially means that your belief is all concentrated on that particular location. So if I give you this snapshot, you're going to say, my belief is 100% at this location. Does that make sense? Very good, right? Now, I have a motion model, which is any distribution. Okay, so let's say that the motion model is a distribution like this. And this is basically, let's say, the velocity distribution PV for that robot. Meaning, or if it's a self-driving car, for that self-driving car, yeah, let's make it a self-driving car here. For this self-driving car, this is the velocity distribution. So the self-driving car would go at 70 miles per hour on average. That's the median, or that's the mean, and then there is a distribution. Okay. So now what you do is you say, I'm going to move each of these particles. This is time one, where you know the particle's location. Oh, let me actually say one more thing. It is possible that you do not know the particle's location initially, in which case you're going to scatter the particles maybe at different possible locations, right? And that would say, look, my belief is scattered, right? It could be here, it could be here, it could be here, it could be here, so on and so forth, right? So you see how particles are capturing your belief. If the particles are spread out a lot, that means your confidence is not too strong. If the particles are concentrated in one location or a few locations, it means your confidence or belief is stronger, right? So for example, you can see my background, right? This is my home. And suppose I tell you, you know what? Suppose I tell you this. I tell you, this is the floor plan of my house. There are windows here. This is a room. This is another room. This is a room. This is a whatever. And there are windows here. And I tell you, from what you can see in my Zoom screen, where would you want to put particles, right? You want to track my location in my room, let's say, right? And this is my initial position, whatever you can see in Zoom. And I'm going to start walking. But you don't know where I am, but you have this floor plan. But you can say, look, it seems like it's a corner and seems like there's a window, right? So maybe you'll put particles over here, one particle over here, right? Maybe one particle over here, one particle over here. This corner doesn't seem likely because there is no window over here. And maybe those are your 3 starting points where you put particles, right? And if you have n particles, then you put n by 3 particles here, n by 3 particles here, n by 3 particles here. Does that make sense? Right? So that's your starting location. It need not be that they're all in one position. And the goal is, as I start moving, these particles will start getting scattered along possible directions, possible trajectories in which I am moving. Okay, we are going to come to that. But all I wanted to say was, it's possible to put all the particles scattered at different places. Very good. Okay. So now, given that you have this velocity distribution, what you do is you take each particle, you sample a velocity from that distribution, and you move it accordingly. So you take each particle over here. This first one, you take a sample from that distribution and you move it like this. The second one moves over here. The third one moves over here. The fourth one moves over here. And after one time step, which means at time step 2, these particles that were here have now scattered over here. And look, the density of the particles follows that distribution of your velocity. Makes sense, right? Very good. So let's write this. You want to move, you want to move n particles based on velocity distribution PV. Make sense? Very good. And now at time t3, you make a measurement of that self-driving car. It could be, let's say, a GPS measurement. Okay. And the GPS measurement tells you that the car is here. This is a GPS measurement. It could be an IMU measurement too, right? It could be a camera measurement from the car, right? Whatever it is, this is a measurement. And you know from the sensor's data sheet that when you make this GPS measurement, the error distribution probability of m given s is this curve. Make sense? Very good. So you obtain sensor measurements. And error distribution P of m given s. So now what you do is you basically update the weight of each particle based on this P of m given s. Which means, what are you saying? You're saying that, look, given this distribution, these particles are likely to have a stronger weight. These particles are likely to going to have a less weight because this probability is so low. In other words, these particles are not agreeing very well to the measurement that I have taken. And so are these particles. Okay. So you update the weight based on that measurement. And therefore, look, this weight is small. These weights become larger. So the size of this circle or this ellipse, essentially, I'm trying to show the weight of that particle as a function of that size. Okay. So what you do is you update weight based on measurement error distribution, PMS. Okay, maybe we should delete this over here. We just say obtain sensor measurement. So far, so good. Guys, any questions? Good. And now you say, look.
Professor, sorry, could I ask a quick question?
Yes,
I'm
yes.
sorry to interrupt you. Did you say, I don't know, I think I just misheard you. Did you say that we measure at time T3? I thought this was like in general, like every time we measure, we do this.
Yeah. I mean, what I mean to say is that this is continuously happening, but 1, 2, 3 are the steps.
Gotcha. Okay. Yeah, no problem. Okay.
Yes.
Thank you.
Okay. So now you've updated. Observe that this weight kind of captures again where your belief is. Right? In fact, it captures better because you've now updated your belief based on the measurement, just not the motion model. Right? This was your belief based on the motion model. This is your updated belief based on the measurement. Right? Very good. And now you say, okay, now it's an important point. Hidden Markov model would have said, I am going to track every particle. Right? Because in the next step, what I'm going to do is I'm going to move each of these particles based on the velocity distribution. But particle filter says, you know what? These particles are very unlikely. Let's kill them. Okay. Which means I'm not going to spend energy tracking those possible paths in the unfolding tree of possibilities. So I'm going to kill these particles, which are very low probability, and these particles, but I'm not going to eliminate them. What I'm going to do is I'm going to bring those particles and scatter them at these locations where I have stronger confidence that the particles that the user is likely to be or the car is likely to be. Does that make sense? Right? I'm saying the energy that I was going to spend in tracking these low probability paths, I'm going to eliminate them, but I'm going to put that energy back in tracking the higher probability paths. Okay. So redistribute. Okay. Now the question is, where should you put these particles? You have these locations to put them into, but should you scatter these killed particles equally across all locations, or should you do something different? Jianhong, I think this is the question. I think your question is what I am. Yes. Jianhong was saying, how do you distribute the particles? And I think that's the thing we are discussing now.
I would say, like, take into account the location of each space, and then put it closer to any like high probability space that it's next to.
Correct. Exactly, Adil. I think that's the intuition, which is a very logical intuition. You don't want to put all these particles over here, right? You don't want to take all these particles and then distribute them equally over these locations. What should you do? You should take all the killed particles and distribute them in proportion to the weights of these particles. So you take the killed particles and you put them at the location of the non-killed particles, the live particles, but the number of particles you put is in proportion to the weight of that particle, that living particle, right? So that's what we'll write here. Redistribute low weight particles at the locations of existing particles in proportion to probabilities. Guys, you realize, right? This weight is actually a probability because it came from PM given S, which we discussed earlier. PM given S should be clear in your mind. Very good. So then what it turns out is after the first iteration, the particles which started over here like this have now come over here, but there are still n particles, right? There were n particles here. Now there are still n particles. But some places have more, some places have less. And now all their weights have become equal because you no longer need weights anymore. The weights was only used to redistribute the particle, redistribute the killed particles. After that, the weights are all the same. You just have n particles. Very good. So let's write that on the right. Still n particles in total, but more particles where belief is greater. Make sense?
Professor, I have a question.
Yes, Adil, go ahead.
I think the way I explained my intuition in number 5 is different from the way that you finally explained the intuition.
Tell me.
So let's say you have like a medium probability space or like a
Let's give it some location names, okay? I think that will be helpful.
yeah, sure.
Let's give it L3, L4, L5. These are all the locations, right?
Now let's say
Yeah, go ahead.
let's say L12. Like say you have like a medium probability at L12.
Is this L12? Let's call this L12. That's what you're
Let's call
saying?
it L12. Yeah.
Yeah.
Let's say we had like a medium probability there.
Hmm.
The way that I kind of explained my intuition was low probability, like the ones that you want to redistribute, low probability areas would probably redistribute closer to like L12, maybe if they were closer to L12 than they would to like L6 or L7. That was my intuition.
Sorry, say that again. At L12, you have a medium probability.
Yeah, so you had like a medium probability, and you had a lot of like low probability points next to L12, right?
That is unlikely, right?
Why is it unlikely that you might have like a non-contiguous? Are you saying it's unlikely that L12 would even exist, or?
No, it's unlikely because where is the probability coming from? The probability is coming from this distribution. Right?
Sorry, could you repeat that?
Oh, where is the probability of these particles coming from? These probabilities, where I'm saying that bigger the circle, bigger the ellipse, higher the probability, smaller the ellipse, lower the probability. These probabilities came from this distribution, Pm given S.
Okay, sure.
Right? So unless this distribution is like this,
okay, yeah, okay,
right, your probability of this one being small and this one being large, that probability is very low. That is not going to happen.
Okay.
Because this is a smooth one. Right?
All right.
So all of these are going to be diminishing probability. So smaller and smaller and smaller. And now you have to choose a threshold. You say, okay, below this threshold, I'm not going to track those possibilities anymore, those particles anymore. So you kill those particles, but you take those particles and you put them back in these locations L3, L4, L5, L6, L7, L8, L9 in proportion to your belief of that location.
Is
the belief of that location is what is the particle's weight at that location.
Is this like a softmax or something, or?
It has some properties related to softmax. Yes.
Okay.
Good. Okay.
I have a short question. Like
yes, Jianhong. Yeah.
Is the sum of the weights equal to 1?
Yes.
Oh, I see. So like
Total
So
probability always has to be 1.
Once you move the particles, then you again remove all the weights. Okay. But you only need these weights when you're doing this one. When you're basically saying, how do these scattering of particles agree to the measurement that I have gotten?
And how do we decide the cutoff threshold?
Yeah, okay, that's art. I mean, you have to say, this is a design question. You have to kind of say that, do I really care about the very unlikely probabilities? For example, I mean, it's a question of application. For instance, right? If you're in the FBI and you're tracking a very important or high threat terrorist, right? And these particles are essentially saying where the terrorist is likely to be, right? If it's a super important thing, then you might say, my threshold is low. I'm not going to kill particles very quickly because I want to also track low probability trajectories of that terrorist. On the other hand, if this application is like, you are tracking a
package.
Huh, John?
Like a package, maybe.
Maybe an Amazon package. Very good idea. Yeah. You're tracking an Amazon package. And it's not such a big deal. FedEx knows that the value of the package is $10. You say, you know what? I'm not going to spend too much time in kind of tracking the very weak trajectories.
Yeah, that makes sense. And do we use a normalized weight to set the cutoff
Correct.
threshold or
Yes.
the
Yes.
normalized?
You will normalize and make it 1. Yes.
Okay. Thanks.
Okay. So the important point over here is the particle started at this initial location. That was where your belief is. And now after first step, the particles are now distributed like this. That's what your belief is. And this belief agrees reasonably well with your measurement and your motion model. Very good. Now what do? You're in the next step. You just do the same thing once again. Now you take the velocity distribution, that PV, and you apply that same PV to each particle. Right? So now you take this first particle, and you move it with the velocity distribution. You move every particle. Right? And which is exactly the same as the second step. It is exactly the second step, but now the particle will move forward. Again, you take the measurement, you update the weights, and you keep doing it. Right? So let's write the right side. Apply motion model PV on each particle and repeat. Basically go to step 2. Okay. So as you can think about, if you visualize it, if I go back to this example, suppose I take a camera in this, suppose I take my laptop right now and I start walking around in my house, right? That's your measurement, right? And you get to see the walls. And you have a model that Romit is walking at some velocity, which is kind of walking velocity, which is maybe, 1 meters a second. Median, and maybe there's a distribution. So as you see the camera view, suddenly you see there is a door, right? So until you see there is a door, the particles are getting scattered. You don't know which way I'm moving, right? So the particles are scattering, but then suppose you see a door and you know that this is a door. This is a door. So the particles are everywhere, but the moment you see a door in my laptop view, you say, this is where Romit must be. So you bring all the particles back here. Right? And again, as I start moving again, you again scatter the particles from there on. So in some sense, the particles scatter, but your measurements bring it back. Your particles again scatter and your measurements bring it back. I hope you see, this is actually hidden Markov model. It's just that you're not tracking all possible scattering paths. You're saying, I'm only going to track n, I'll track the best n paths. Guys, I hope that made sense. Very good. Okay, so observe that there are always n particles. Which means what? Your CPU load is fixed, right? The number of particles is directly a function of your CPU load. Or your CPU load is directly a function of the number of particles. Second observation, scattering of n particles captures my current belief. Current belief of Sk. Do you agree? At any point in time, if you see the scattering of the particles, that's what your belief is. Finally, particles are like magnifying lens or clones of that user or of that object that you're tracking, right? It's like cloning, and the clones spread out when you don't have good confidence. The clones all come together when you have strong confidence. So it's like a magnifying lens or clones. You allocate more particles to places, trajectories that you want to search with high resolution. Does that make sense? Suppose you're an FBI, okay? And you're tracking this threat, this terrorist who's moving around in the country, and he's a smart guy. He moves around, and your particles is tracking all the possibilities. He could be Illinois and Chicago. He could have gone to Wisconsin, and he might be in Madison. So your particles are scattered. Okay? And then a smart intern comes in and says, you know what? I think for some reason, because of this person's family connection, blah, 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 there's a possibility that that person is at St. Louis. I think we should track the St. Louis possibilities, where all he might be going to St. Louis. What do? You say, yeah, okay, that's an important piece of information. Maybe the possibility of him being in Ohio or Michigan is low. Let me take some particles from Michigan and Ohio and put them in St. Louis. Right? So that in St. Louis, those particles can track those possible paths or possible trajectories, or those possibility tree. Right? So wherever you put particles, you have the ability to basically trace the possible trajectories. Wherever you're not putting particles, you're saying, I'm not going to trace those. I'm not going to track those. Right? So particles are like a magnifying lens. Wherever you want high resolution tracking, you put more particles. Wherever you want low resolution tracking, you take particles out of it. Lucas says on the chat, the family information is like a measurement, right? Yes, the family information is like a measurement, or it's like a prior information. Yeah, it's like a measurement. Yeah, you can say it's like a measurement. Yeah. Very good. Okay. So observe also, now we are connecting it to hidden Markov models, particle filter operating on continuous space. You see, right? There's no more discretization anywhere because you're just moving the particle in a continuous space. Second, any kind of motion model can be incorporated. Any motion model I can put in right now. You give me a differential equation of the acceleration of the velocity. I can basically, from that equation, all I need to do is, given these particles, I need to figure out how these particles should move. So any motion model I can incorporate. Third, noise can be modeled. So this noise I can model. So any F and G possible, even if non-linear. So look, any F, any G, any N, I can now model, because I'm now basically moving the particle based on F, G, and noise N. Very good. And finally, CPU load is a function of N. So you can choose N based on system resources.
A quick question, like
yes,
why the number of particles is fixed, and like why don't we like cut off, like have a cutoff threshold and eliminate some particles?
Yeah, but if you have the CPU, why not? Basically you want to fill up your CPU. Right? So you want to use as many particles that your CPU can support.
But like after we delete, like for instance, like 2 particles, then we become like n-2 particles. And how do we make it to like n particles?
Oh no, you're not deleting, right? Remember, we are saying that we are moving these particles. These particles that we killed, we did not remove them. We are bringing them back into these locations.
Oh, I see.
So I think the word kill just sounds kind of permanent.
Okay, sorry. It's not killed, it's move or redistribute. Redistribute low weight particles to the locations. Maybe I should say to the locations of existing particles in proportion of probabilities. Jahang, does that make sense?
Is it just like a sampling
It's
process?
like a sampling. Yes, yes.
Oh, I thought previously was like we normalize the weights with the remaining particles.
No. The number of particles is always the same.
Uh-huh. Ah, I
You're
see.
FBI, you're tracking this terrorist suspect, and the particles are like, there are a lot of particles in Chicago, some particles in Champaign, some particles in Peoria. And you realize that the particles in Champaign, those probabilities are very low. You take those particles and you put most of them in Chicago, because Chicago probability is high, and you put a few in Peoria, and again you start tracking from there.
And for instance, if we move like 6 particles into the middle part,
Right.
Do these particles have the same weights?
Once you've moved them, you move them in proportion to these weights. But once you've moved them, all of them have the same weight again. Basically, all of them become, there's no more weight anymore. They're all just n particles.
There's no weights.
Yeah. You need the weight only when you use this distribution. You need the weights to figure out how you are going to move these killed particles or these low weight particles into these locations. There you need a distribution. That's why you need this weight.
So like for instance, here in L6, it's like it has like a more weight than the other particles, right?
Correct.
So in the step 6, this one particle will become like 3 particles, right?
Okay, let's put some numbers just to be even more clear. Let's say out of these L3 to L9, this is 0.1, this is 0.15. Okay, no, wait, let's do this. This is 0.05, 0.1, 0.2, 0.25, 0.25. Guys, tell me how much more do I need? 0.5, 7, 8. 1.5, 0.5. Did I make it up? Is that 1?
The last one can't be 0.5.
Sorry, 0.05, I mean.
Do we need to make it 1?
Yeah.
Oh, after like all the particles move into the middle. Okay.
Yeah. Okay. Now suppose you killed 100 particles. So you take out of those 100 particles, you put 5 at this location L3. You put 10 at this location L4. You put 20 at L5. You put 25 at L6, 25 at L7, 15 at L8, and 5 at L9.
Okay. So in a new L6 location, are there like 26 particles, right?
Correct.
Like the original one plus the 25.
Correct.
Oh, I see.
And then you forget the weights because now you have this distribution after you've moved the particles.
Oh, this is clear now.
Good.
So if I can just clarify,
yes,
number of particles at each L location is just a function of the weight times the number of particles that were killed?
Correct.
Okay, all right.
I don't understand why we need to scatter the particles. It seems that if we only have the measurement, we can also do the redistribution.
Oh, because the scattering of the particles comes from this distribution. If you did not scatter, right, you would not get these particles. If you did not use the PV, you won't be able to scatter the particles.
You mean this scattering has affected the later distribution before we distribute these particles?
Sorry, say that again, Hafan.
You mean the scattering step would affect the particle distribution before I redistribute the other particles?
Right, because if you do not scatter, this distribution could have been here, could have been here, could have been here. You don't know.
But measurements can tell me that.
No, but you also want the probability, the the PV, the motion model to also play a role, right? Suppose the motion model gives you this scattering, but then the measurement comes up over here. This is where the measurement is instead of this, let's say. So then you know what will happen. Then you will have your distribution somewhere here, which will try to agree with the motion model and the measurement.
So the final distribution is the combination of the PV and the PM.
Correct. Exactly. This distribution is a combination of the PV and the PM given S.
How is the combination works? Is multiplies or just times together?
Oh, we do hidden Markov model.
Oh, I see.
Right? We do joint estimation of all of them.
Yeah, that makes sense.
Perfect. Okay. So very good. So that gives us Kalman filter, and you choose N based on how much CPU you have. Okay, if you have a supercomputer, you can choose large N. If you're running it on a mobile phone, you choose small N. Very good.
I hate to do this again, but
yeah, go ahead.
I don't fully understand why this is a continuous space. Why is space not being discretized here?
Okay, I don't want to discretize space. That's the first answer. Imagine a self-driving car moving. Space is not discretized. So what you say is, if this is the initial location of the car, this is your home garage, and I know the velocity distribution of the car, you say, okay, let me sample one velocity from this distribution. I sample maybe this value, velocity. Let's say mean is 70 miles per hour. I sample a velocity from the distribution that gives me 65. So in one time unit, I move this much at 65 miles per hour. Then I take the next particle. I sample once again. That gives me 73. I move this particle, the second particle, as if at 73 miles per hour, how far will it go in 1 second? I move it that much. I do every particle accordingly. So it essentially means after 1 second, if this car was moving at this distribution, where are the likely positions of the car? And the likely positions of the car is going to mimic this velocity distribution, right?
Okay.
Right. Very good. Okay. So, and the last point I want to make is, so particle filters gives you this very general, very flexible framework, any F, any G, any noise, nonlinear, etc. But in certain applications where F and G are linear, if F and G are linear and noise is Gaussian, then things become even easier. Things actually become very simple. The whole math becomes very simple. We'll not get into that. And that is called the Kalman filter. We'll not get into that, but it's a kind of a special case of particle filters where things are easy. F and G are both linear and the noise is assumed to be Gaussian. So this is what where we're going to let go of particle filter and Kalman filter. And quickly, I want to kind of tell you about this very popular thing called SLAM. And again, I want to just give you an intuition. By the way, there are some YouTube videos on the website, so feel free to go and actually, I encourage you to go and look at those videos. It might give you even better intuitions, animations and stuff. So the SLAM problem is the following problem, which is very related to particle filter, Kalman filter, hidden Markov models. But the problem is, imagine there's a Roomba which has a camera, okay, or has a LiDAR, okay, and the Roomba is walking around in a house, in a building, in your apartment, let's say, and the Roomba's camera is looking at, Roomba's camera has a field of view. Okay. And so at some points it's looking at a chair and a table. At some points it's only looking at the chair. Some point it's only looking at the table. Sometimes it's not looking at either of them. And now the question you have is, can you figure out both the trajectory of the Roomba, basically the Roomba's location, as well as the locations of the chairs and tables in your apartment? So this is simultaneous because you want to do the Roomba, you want to get the Roomba's location, and you also want to get the object locations in the environment, which is the map. And I want to do this in 3D. If I can do this in 3D, I basically know what the environment, the Roomba knows what the environment looks like, and also the Roomba knows where it is. Okay. So this is the simultaneous localization and mapping. So the main goal is, can I compute both the sensor location, which is L1, L2, L3, L4, and the visible objects location, which is L10 and L11, L10 and L11. I want to get both.
It seems like this would be useful.
Yeah,
because any measurements you can get about either location or objects locations, those let you infer things about the other. They're related.
Totally. And this is what self-driving cars are using. This is what Roombas are using. Many today's technologies are basically using SLAM. While a car is going, it's figuring out what its location is, and it's figuring out what environment it's looking at. In fact, a Roomba, so here is a Roomba's reconstruction of the environment, where this is the Roomba's trajectory, and this is the map that it has created. In fact, today's Roombas do this. So first time when it goes into your house, you start it, it'll actually go around the house and it'll map out the house and simultaneously map out where it is, where it is itself. Okay. So the SLAM algorithm, again, if you understand hidden Markov models, you have all the ammunitions to attack to understand SLAM. Okay. The SLAM algorithm takes two inputs. One is continuous, let's say, pictures of objects. And it need not be pictures, it can be other RF signals, RF Wi-Fi signals, it can be LiDAR, it can be sound, whatever. Right? And it also takes a motion model. Of sensor. Right? And it outputs sensor trajectory, which is basically the location, and object locations, which is basically the map. And the intuition is actually very simple. The intuition is, I don't know where I am. I don't know why the objects are, right? My goal is basically, what is my goal mathematically? I want to get probability of S1 through N of the sensor and S1 through K of the object given M1 through N of the measurements. Let me say that again. These S1, S2, S3 with superscript S, let's make it superscript C for camera. Let's make it O for object. I want to get my camera location from time 1 to time N and my object locations from time 1 to time K, or maybe even let's make it time 1 to time N, given the measurements M1 to Mn. Does that make sense? This is very similar to hidden Markov model, except that now we've also introduced a state variable for the map, for the environment. In hidden Markov models, we talked about we did not have this. Remember, right? This is hidden Markov model. If you take away the object locations, right? Now I'm bringing in the object locations and I'm trying to solve everything together. And the key intuition is, look, if I am at this location, I don't know, but let's say I am at this location L1. Then I see the chair and the table at some angle, at some perspective, right? Now, if I move to L2, I should see the same chair and table at a different perspective, right? So when my camera measures the change of perspective, it gives me some information of how much I must have moved, right? Suppose I take a picture of a chair and table, and then my next picture is a 2-degree 3D orientation shift of that same chair and table. That tells me something about how much I have moved. I couldn't have moved hugely, right? And now the motion model that I have tells me how much I have moved. So the rotation of the view tells me how much I moved, and my motion model tells me how much I've moved. I now have to make them agree. Now I do not know what the object's location is, so I say which object location and which of my motion together agrees most with my IMU and my camera view, or my IMU motion, or my motion model and my camera view, right? Basically what you're saying is the views that you have from every location are correlated, right? There is some dependency. If you watch the chair and the table from each of these red locations, red points, you're not going to see independent things. There is a correlation in the view that you're seeing, and that correlation can help you understand where you are and where the objects are, right? There's like a dependency graph. Okay, that is what they do, and as a result, they get this sensor trajectory, and they also get this, which is the object location or the map. Okay, the math has very strong similarity to hidden Markov models, but again, you have to just account for this additional object. This is a high-level intuition. I've put a video of SLAM, a MATLAB video of SLAM in the website. Feel free to look at this, but that is where we will stop. Questions? Very good. If there aren't any more questions, then we are ready to move to the next. Oops. To the next topic, which is around acoustics. But before we get to acoustics, we need to do a little bit of math once again, foundation math, and around optimization. Guys, any questions from SLAM? Does that make intuitive sense why you can do both? Right. Good. In fact, suppose your wall is a big TV. Yeah, maybe this is a good way to ask, or a good way to think about it. If your wall is a big TV and there's something playing on the TV, the Roomba will go crazy. Why? Tell me why.
Basically, things are like, if it can see the images,
right?
Like, let's say the Roomba is staying still, things
Right.
on the screen might be moving, and so that might it doesn't really match up with the motion model. Basically, it has unexpected changes of perspective.
That's true. And not only that, the Roomba, if it is moving, it expects that if it saw a chair from an angle theta, it expects that when it moves, it should see the same chair from an angle theta plus epsilon. But if the wall screen changes to something completely random, that you're playing a James Bond movie on that screen, James Bond was on the beach, and in the next time unit, James Bond is in a car chase. The Roomba has no correlation from which it can say, I must have moved this much and the object must have been here. It cannot do anything like that. Okay. So the whole point is every measurement that I'm making about the environment are correlated. And that correlation gives you the opportunity. Very good. Okay. So we are going to get started with basics of optimization. Again, nothing deep here, but something that we would need, and something my feeling is you've already seen these. So this is going to be boring, but if you've not seen them or if you're forgotten, maybe this is a good brush up. Very good. Optimization. What is the big goal? The big goal is I am given a graph, a function, and I want to find extremums, extreme points. What are the extreme points here? This is an extreme point, 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 this is an extreme point. Extreme points are points around which, in the neighborhood of which, all other points in that function are either greater or lesser. That's what's called an extremum. Okay. So how do you find an extremum? You remember from calculus, you differentiate df by dx equals 0. That gives you local extremums. Guys, you remember? Right? You differentiate, you equate it to 0. That gives you local extremums. How do you know this extremum is a maxima or a minima? And the way you do it is that once you get some x star from here, x star such that dfx star by dx equals 0. Once you get an x star from solving df by dx equals 0, then you put that x equals x star in a double differential d2f by dx square. And if that is greater than 0, then you say that is a maxima or a minima. If the double differential is greater than 0, then it's a maxima or a minima. Jianhao says it's minima, and that's correct. Oops, sorry. Okay, so this is basically d square fx star by dx square greater than 0. Very good. Now, in this lecture, we are going to move one step forward and say, look, what happens in the previous case, x and fx, or rather fx was a function that is r to r. What does that mean? That means x is a one-dimensional variable and fx is obviously always a one-dimensional, or typically a one-dimensional variable. But what if x is a vector? That is, what if the domain of the function is a vector, that is, x is a vector, which means f can be thought of as a function from Rn to R. Right? So in this kind of a situation, maybe one way to think about that is here is a function where this is x1, this is x2, and here there is a function that's kind of a weird bowl. This is fx. And x is now a two-dimensional vector. So this f is basically R2 to R. Guys, you're all with me, right? How do you find the minima for this kind of a shape? Right? Same thing. Now what you do is you use this operator called del, which is also called nabla. And you say that del fx is basically partial derivative of f with respect to x1, partial derivative of f with respect to x2, and so on, partial derivative of x with respect to xn. So del fx, okay, takes a function and gives you the gradient of that function for all the dimensions. Yes, this is gradient. Okay. It gives you all the dimensions in which f is changing, and each of them tells you at what rate f is changing along each of these dimensions. Okay. So the del operator, you can think of this as takes a function as an input and gives you a vector as an output. The vector is in n dimensions. Is that clear, guys? And that vector is easy to calculate because you basically differentiate that function with respect to each of the variables in that vector. Very good. So if you now equate this to 0, del fx to 0, you get the extremum points. But now you have to find minima or maxima. Now how do you do it? So, okay, over here we double differentiated. We'll do the same thing, del square fx. But what is del square fx? Well, del square fx is the following. You say del f del x1 del x1. Then, because it's a vector, you have to do del square f by del x1 del x2. And you keep doing that del square f by del x1 del xn. Because once you've taken the derivative with one element of that vector, you have to take the derivative of that with all the other elements, right? What is the second row, guys? Del square f divided by?
Is it del x2 and then del x?
Correct.
Del x1, yeah.
Yeah. Del x2, yeah.
Who knows what this matrix is called?
Jacobian. Jacobian matrix. Okay, right.
Careful. Laplacian. No, this is called a Hessian matrix. Yeah. Okay. Good. Now, look. Yeah. Okay. So how do we find a local maxima minima of such functions of vectors? Right? Let's say here is a function which is a function of x1 and x2. And we want to find the local maxima minima. Okay. We know that delta fx equals 0 gives me extremums. Right? So delta fx equals 0 will give me this, will give me this, and will give me this. It will give me these 3 points. in X. But which one is a maximum, which one is a minima? And now in one-dimensional case, we took the double derivative and we looked at whether the double derivative is positive or negative. But in this vector case, what does it mean that the matrix Hessian is positive or negative? What do you mean by a matrix being positive or negative? It doesn't make sense. Okay. In the vector case, what you have to do is you have to say this matrix is what is called positive definite matrix. So this means that the Hessian has to be a positive definite matrix for that X star to be a minima. So when del square fx star is a positive definite matrix, this indicates minima. Remember, del square fx star means you compute del square f and then you plug x star into that matrix, right? And then you check for whether that matrix is positive definite. Okay, so what is a positive definite matrix? This is something that comes right after eigenvalues, eigenvectors. We did not talk about it, but I just want to give you the definition of it. A positive definite matrix is when a matrix A is positive definite when all the eigenvalues of A are greater than 0. All the eigenvalues of the matrix A. Remember eigenvalues, guys? Ax equals lambda x. All the eigenvalues are greater than 0, then it's a positive definite matrix. Another way of saying it is, or x transpose Ax is always greater than 0 for all x. So any vector x you take and you multiply A with x transpose in the beginning and x at the end. Guys, what will this be once you do all x transpose Ax? Will that be a vector or a scalar? Remember, x transpose is this column, sorry, this row. Then there is this matrix A, and then there is this vector x. So x transpose Ax is a
scalar.
Very good. Okay. Right? Because this multiplication is a vector and row times column is a scalar. Right? Very good. So this is a scalar. That you can compare with 0. Okay. So there are many ways of checking if a matrix is positive definite or not. Now, there's another word I just want to introduce because it's relevant. Positive semi-definite, PSD. A matrix is positive semi-definite when lambda I of A, all eigenvalues of A are greater than or equal to 0, or x transpose Ax is greater than or equal to 0 for all x. Okay. You'll see many applications if you go into advanced grad school and masters and all of that. If you take advanced courses, you'll see that positive definite, positive semi-definite matrices play a huge role in many algorithms and techniques. Okay, very good. We just want to know this by definition at this point. So note delta square fx star, if that is positive definite, then that's a minima for sure. If it is positive semi-definite, then it is not sure if that is a minima. In other words, positive semi-definiteness is a necessary but not sufficient condition. In other words, let me ask you this question. Let's go back to a single one-dimensional x. D square f by dx square, x is one-dimensional. Suppose I say this is greater than 0 at x star, at x equals x star. I say that this is greater than or equal to 0. Can you say that x star is a minima? So in other words, to verify if x star is a minima or not, do you need this to be greater than 0, or can it be greater than or equal to 0?
Greater than, right?
It has to be greater than 0. Can you give me a case where if it is greater than or equal to 0, but it's not a minima? Can you give me a case where delta square f is greater than or equal to 0, but it's not a minima? Okay, maybe.
So that means the second derivative is like a flat.
Ah, that's a good one. Yes, that's true, right? You can just take the x, you can just take function fx as x square. Del fx is 2x. Del square fx is then del square fx is 2. So give me a different function.
I think if you start with a flat line, it works.
Oh, I see. So you're saying start with 2x.
I think so. I think that might work, right?
Yeah.
So I think the flat line doesn't work because like all points are minimizers.
Correct.
Right, like all points are its minimum.
When you solve 2x equals, when you say 2x, let's say the fx is 2x. You take a derivative. Fx is 2. Del of fx is 2. Right? Fx is, let's say, 2x. So df dx is 2. Right? So you cannot find a minima in that case. That's a good point. So give me another function. Okay, maybe you don't have to give me. I'll give you one. Let's take x cube. Okay. Del fx is 3x square. You equate that to 0. Your x star, your extremum, is 0. You agree? Very good. But is x star a minima or a maxima, or is it neither? So let's check that by doing a second order derivative. So del square fx star is nothing but 6x star. Right? Which is 0. If this was true, then this would mean that x star is a minima. Guys, are you with me? Right? If this was true, if this was greater than or equal, then hey, look, this satisfies this. So then this must mean that x star is a minima. But let's graph it. Okay. What does x cube look like? X cube looks like this. Okay. X star equals 0. X star equals 0 is this point. The center, this point. That's not a maxima, that's not a minima. Right? So x star equals 0 is not or neither maybe. A minima or a maxima, right? Because this is delta square fx star equals 0. Okay, so x star 0 equals 0 is not maxima or a minima. This is called a stationary point. Meaning this x star is a point where if you drop a ball, let's say x cube is that curve. If you drop a ball exactly at that x star, it's not going to move. But it is not an extremum. Right? So when this del square fx star is equal to 0, you are getting a stationary point, but you're not getting a maxima or a minima. Okay? So bottom line is del square fx has to be greater than 0, and that is a sufficient condition for finding maxima or minima. Sorry, that is a sufficient condition for minima. And del square fx less than 0 is sufficient for maxima. Guys, any questions?
Yeah, how about in the case of x to the fourth? It's going to be the same thing, but it's also going to be a minima, right?
X to the power 4 is going to be a minima, but remember x to the 4 is like this. So it is
okay, so that's why we say it's like a sufficient condition, right? Or not sufficient condition.
Yeah, I mean, yeah. In the case of x to the power 4, one second, let me. In the case of x to the power 4, your del square fx is going to be 0, right? But you need one counter example to say that it's not a sufficient condition, right? In this case, it holds, but that doesn't mean it's true. Eric, does that make sense?
Yeah. I think I understand that. So it could be, but then you have to evaluate it to see if it actually is, basically.
Right. So delta fx is 4x cube. Delta square fx star, 4x cube, if you equate it to 0, your x star is equal to 0. Then delta square becomes 12x square. If you substitute x star equal to 0, that will become 0. So you are getting del square fx equals 0, but it's still a minima. Right? So it's a necessary condition, but not sufficient, because I've come up with one counter example where I showed you that a non-minima was also satisfying the condition that del square fx equals 0.
Okay, so if we actually want to know, like just by taking the gradient is not enough. So we have to use other conditions like the slope or something to actually evaluate if it's actually minima or not.
Absolutely. And this is the sufficient condition. Okay, good. Little bit more, and then we'll stop. Delta fx equals 0 and delta square fx positive definite gives us local minima. Because if you take this graph, if you take this function, you're going to get delta square fx positive definite for this point and this point. And of course, delta fx will be 0 at this point and this point. So you're going to get local minima, not a global minima. Okay. But how do I get a global minima? Well, for general functions, any shape, it's hard to get a global minima. Okay. But if a function is a convex function, then local minima is the global minima? Okay. So we are saying, look, we don't have an answer to the question, how do you get a global minima? But for certain kinds of functions, if I get a local minima, I can say that that itself is the global minima. So then the question is, what is a convex function? Okay, which is the special class of functions in which local minima is good enough to get the global minima? Okay. And intuitively, or very loosely, functions that have an upward curvature everywhere is called a convex function. Okay. Upward curvature everywhere. So here is an example of a convex function. This is a convex function. This is a convex function. This is a convex function. All of these are convex functions. Look, anywhere you look, it's an upward curvature. We're going to make this formal very soon. So what is a non-convex? Right? If you look at this part, this curvature is downward. Okay. All non-convex. Because it does not have upward curvature everywhere. Very good. So intuitively, how do you capture curvature, upward curvature? One way to say upward curvature is the following. If I take 2 points on that function and I join a straight line, that straight line will always lie above the function itself. It's like if it's like a bowl, you put a stick inside the bowl will always be below the stick. If the bowl had some downward curvature, you will not be able to satisfy that property. Right? In other words, take any 2 points in a bowl and put a stick along it, and if that stick is always above the bowl, right? But if you think of this function, you take this point and you take this point and you put a stick in it, that stick is not going to be contained in that bowl. Right? Yeah, if you take this function and this point and and you put a stick, yes, the stick is contained inside the bowl, but that's not true between this and this. So a convex function is where the stick has to be contained inside the bowl for regardless of any 2 points that you choose inside the bowl. Okay. So the straight line joining any 2 points fx1 and fx2 always lies above fy, where y belongs to x1, x2. Make sense? Very good. So we can write this mathematically. Mathematically, what do we want to say? We want to say, look, any point on this stick should be greater than the corresponding point on the function. So how do we say any point on that stick? Any ideas? How can we, given this fx1 and fx2, these are the 2 points, how can we express any point on that stick? How do we express the midpoint of that stick?
It's like the average of the 2 points.
Average, right? So the midpoint will be half of fx1 plus half of fx2. Agreed? Now, how do I express this point? Or how do I express any other point? Well, I can say this. I can say alpha times fx1 plus 1 minus alpha times fx2. Right? If alpha is less than 1 or less than or equal to 1 and greater than or equal to 0, then look, I'm taking a weighted average of those 2 points, fx1 and fx2. Does that make sense? And I can, you give me any point, I will come up with a corresponding alpha. Right? At the extremes, fx1 and fx2, alpha is 0 or alpha is 1. So this left-hand side, this gives me the ability to model any point on that line. And that should be what? Can someone say that should be greater than or equal to what? That should be greater than or equal to the corresponding value of the function. So how should I write that?
For all y, f of y between x1 and x2.
That's true, but I need to write that mathematically in an equation. What is this point? What is this point? The corresponding point over here, what is this point? This is alpha x1 plus 1 minus alpha x2. Agree? So all I need to say is this should be greater than alpha x1 plus 1 minus alpha x2. Guys, does that make sense?
Yeah.
Very good. This is the definition of a convex function. Okay, very good. So now I've told you what is a convex function. I've given you a mathematical definition, and you're going to ask me, okay, fine, but someone gives me some function. How do I know this is convex? Do I go and test for every x1, x2? I think that's one way of doing it. You go to a computer, you randomly generate different values of x1 and x2 and keep testing. But you may miss out some x1 and x2 for which that convexity may not hold. Right? So is there a clean way of saying this is a convex function? And it turns out, you're not going to get into the proof, if the Hessian of that function is positive semi-definite, that is good enough. That tells me it's a convex function. So it's a necessary and sufficient condition, meaning if it's a convex function, that Hessian will always be positive semi-definite. If the function has a positive semi-definite Hessian, it has to be a convex function. So this implies both ways. This is both ways. Okay, that's good. So look, if I give you a function, you first check if it's convex. If you see it's convex, you take a single derivative. You get x star by equating that derivative to 0. And that x star must be the
global minimum.
Global minima. You don't have to check for minima anymore because you've checked it's convex, and that check already tells you that it is a convex function. Very good. Okay. Now okay. So given fx, if delta square fx is greater than is a positive semi-definite, positive semi-definite Hessian, then fx is a convex function. Thus, fx equals 0. Oh, sorry, del fx equals 0 gives global minima. But here is the bad news. Even if fx is convex, in many cases, it's difficult to solve for delta fx equals 0. Right? Convex or not, you still have to solve delta fx equals 0. That is hard, some cases. For example, if fx is e to the power x plus x square, it's not easy to solve delta fx equals 0. Okay. So closed form solution is difficult. As a result, we need to solve functions iteratively. What does that mean? We will look at this function. We will start from some x0 and we'll try to move closer and closer towards the minima. That is iteratively. I cannot come up with one shot closed form answer. And this motivates what are popularly known as gradient descent methods. Make sense? That's where we'll stop today. And next class, we'll continue with basically doing gradient descent, steepest gradient descent. And then we will talk about how these gradient descent algorithms are actually useful in noise cancellation. And you'll see how they're beautifully connected and how noise cancellation in these Bose earphones and stuff actually uses a lot of these math that happens in optimization. Okay, I'll stop there and I'll of course hang back for questions. Class is over. Questions? Thanks.
Thank you.
Thanks.
Thank you.
Thanks, Eric.
Professor, have a good one.
Yes, you too, Lucas. Bye. Okay. Seems like no questions today.
Can you hear me?
Yes, Adil, I can hear you.
Yeah, I kind of had like questions during office hours, if that was okay.
Sure.
Give me 1 second. I'm just going to switch to my other computer.
Sure. I'm going to also be back in 30 seconds.
Okay.